Welcome back. We are talking the thing that I continue to call network calculus. Let's very quickly. Oh, that's not what I wanted. Refresh what I was doing this morning. So, this is something I've been talking about for a few days on stream. You can go back and check some of that out. I'm trying to collate it all on YouTube so that it's at least kind of findable. But basically, the very broad brush of it is I'm working out neural networks and all the black box deep learning systems that we are using all the time. Even if you're not, like, most people who come across this won't be coding in these systems, but they will tend to be the subject of them all the time. If you're watching this on, well, actually any platform, if you're watching it on Facebook, if you're watching it on YouTube, if you're watching it on Twitch, it is a neural network that is deciding to show it to you. And something that I think CGP Grey, let's just write that quickly, you can find him on YouTube, CGP Grey. I recommend their videos a lot. No idea what it stands for. Central George Project. Expresses this very well. Just be like, no, that algorithm that's deciding what you see, that's deciding what your take on the world is, what are the elements from which you build up your picture of reality. Nobody understands it. This is, when it first really clicked with me, I was like, this is gross, this is insane. And it sort of is. It's not fully not understood, like everyone knows how, it's perfectly easy to know, to work out. I've got to stop using this language where I'm like, everyone, perfectly easy. With some work, you can work out how it works, but no amount of doing that will help you translate it. But I'm starting to put together effectively a programming language in the base building blocks of these neural networks to be able to ask the question of, like, okay, I have no idea how close it is, but what is the optimal way to do this process with a network? So, starting to build up a little library of functions, where the basic idea is that at every step, we take some inputs, we put them through some functions, and we get, I don't know where outputs has gone, and we get some outputs. Each function, actually, to be a bit more exact, each function can only give one output, but it can take multiple inputs. And the way it takes those inputs is it works out the weighted sum of all the things coming in. So, the sum of everything coming in multiplied by the weights. And the way that I'm expressing this is any number above, these are the lines, they're always going to feed left to right, and any number above the line tells you what weight we're multiplying this particular input by. I'm not allowed to draw on this one. Fair. So, that's, I don't know how coherent that is, but that's as much of a catch-up as I'm going to give you, and then we're going to carry on with where we left it. So, one thing that we're using a lot here is that if the thing that we're passing to these functions is small, we can Taylor expand and therefore pick out values that way. So, everything in this calculation is still a sigmoid, so sigmoid looks like this. And we want to find these coefficients of the Taylor expansion, so we've got to do that by differentiating. Oh, this is probably some nasty calculus. So we've got 1 over 1 plus e to the minus z minus z minus e to the minus z plus e to the minus z over 1 plus e to the minus z squared, which is not a particularly nice thing. I could write it as theta over z plus theta squared e to the minus z over z. Oh, I've done the thing again, and I said I was going to not do this, where z is unitless. This is very much me coming from a physics background. It's really useful to keep the units for things. So actually, we're going to say it's z over a over 1 plus e to the minus z over a. Which means d sigma by dz is, this is still just going to be sigma over z. Yeah. Plus sigma squared. I'm just doing this in my head at this moment, so apologies if I get it wrong. E to the minus z over a over z. Let's do it properly. Right, what have we got? We've got 1 over a, 1 plus e to the minus z over a plus z over a. Oh, this is over a. Oh, I'm confused. Z over a minus 1 over a e to the minus z over a minus all of that 1 plus e to the minus z over a all squared. So let's just pull out the sigma theta. Again, no promises ever to be consistent about names of Greek letters. Plus theta e to the minus z over a plus e to the minus z over a. Or we could write that a different way as theta over a gonna put everything over this guy. A, oops. Plus e to the minus z over a. I could probably go with a slightly thinner pen, couldn't I? Starting to get the accuracy in. Plus e to the minus z over a And then we're going to have a over z plus no, this doesn't really get any. This doesn't get much better than that. It's not going to cancel out into anything particularly nice. It's also kind of a stupid way to put it because I can't evaluate this at 0. So let's just do it. Ooh, not that. So I can put the whole thing over 1 plus e to the minus z of a squared. We get 1 plus e to the minus z over a minus plus z over a. Some days your brain just ain't in it. Z over a squared. Yeah? Yeah, I think so. So this means that, so this is sigma 1, this is sigma naught in terms of z. Writing this, I'm starting to have a newfound respect for people who write like maths notes. Like, there's so many concepts that you don't want to overload at once. So sigma naught at naught is naught. Sigma 1 at naught is a half. We've already seen this, but we are going to have 2 actually it's going to be 1 over 2a, isn't it? That's going to disappear. So we're going to have 1 over 2a. Am I happier now that I've got this extra factor? Maybe I'm not. Maybe I don't want it to have units. Actually, I don't. I don't think I want it to have units. That unit can just be changed by changing all the weights. And because the weights are unique to a node, there's no real cost to doing that. Alright. I'm going to do this again from scratch. We're going to work this out more fully, but also we're going to be non-dimensionally consistent because Z has no dimension in a network. So sigma naught is alpha over 1 plus e to the minus alpha. Sigma 1 alpha is, we just had it, it was over 1 plus e to the minus alpha squared times 1 plus e to the minus alpha plus alpha. I think so. sigma 2 alpha, so that's just another derivative, is minus 2 plus e to the minus alpha cubed minus e to the minus alpha. Oh, that's e to the oops. Then the thing in square brackets. I'm going to rub this out again in a sec. I'm just going to work the whole thing out first. Plus 1 over this squared. Minus alpha minus alpha plus alpha. So that is equal to 1 over brackets cubed. Let's do this one first. This is just minus alpha e to the minus alpha bracket. And then this one is minus minus is plus, plus 2 e to the minus alpha previous square bracket. And now this is the kind of thing that would give your poor maths teacher nightmares about the working from the line before. If I make a bunch of mistakes on stream, then that at least gives viewers something to do. Which is obviously why I'm doing it. No, I'm just scruffy. 1 over 1 plus e to the minus alpha cubed times, let's start with this, 2 e to the minus alpha plus e to the minus 2 alpha 1 plus alpha 2 times that, minus alpha e to the minus alpha plus alpha e to the minus 2 alpha. It's actually a really bad habit rubbing out that working. I need the equivalent of scratch paper because 2/3 of the time I have to go back and check something. Do any of these cancel? So we have e to the minus alpha 2 minus alpha plus e to the minus 2 alpha plus 3 alpha. No, that should be minus 2 plus alpha. No, that did not work. I was like, I can save time. 2 plus alpha. So, what do you actually get when you put in alpha equals 0? You get that sigma naught of 0 equals 0. Gamma, it's gamma. Gamma 1 of 0 equals a half. Gamma 2 of 0 equals was 1 over 2 cubed times 4, also a half. This, by the way, is something that I can just plug straight into Wolfram Alpha, which I'm going to do now. Just to check. anyone who is watching is a parent who's unsure of whether or not, I don't know, I probably shouldn't be giving parent teaching tips. I'm not a parent. If anyone is watching in general who is unsure whether or not it's healthy for learning to use structural backup tools like Wolfram Alpha, I advise it as long as you're always using them as part of the route to an answer, not the answer itself. So, y equals x over 1 plus e to the minus x. I don't think I have to use x here, but I don't want to confuse the thought computer. Come on, give me the expansion. Why aren't you giving me Taylor expansions? Is that what I've got? Here we go. One plus e. Oh, that's e minus x. That makes sense of it. Okay. Quarter, a fourth. So I've got something wrong with the second derivative. So you can sort of see how this function is working here. Like, it is so close to a value and it gets to it as soon as you zoom out. This is much more zoomed in than this. So that is what I had for thing mode. God. Nice and clear. So I should be getting a quarter for that. Why am I not getting a quarter? Well, let's do it again. This time maybe let's keep the working. It's possible it was fine and I just missed it, but I like to, if I'm ever unsure, just start from scratch and be certain. And I think that's a good habit to get into. So, again, let's use this kind of approximate language where we're going to get a minus 2 times minus alpha. No, sorry, just times minus e to the minus alpha. That's the derivative of this. Oh, no, that's the derivative of this times the square brackets plus the curly brackets. What are they called? Parentheses. Derivative of this is, let's put it in these, but e to the minus alpha minus e to the minus alpha 1 plus alpha. Okay, so I think I lost a term here before because actually this is just minus alpha times that. So we end up with 2 e to the minus alpha for this cubed times square brackets plus, let's bring out the curly brackets here, this cubed alpha e to the minus alpha. That's from these, this is negative. That's from this alpha here. These two cancel. times parentheses. So 1 over parentheses cubed two e to the minus alpha. In fact, let's just pull an e to the minus alpha out the front. There's one and everything. Don't need it. Well, we need it, but we can separate it out. 2e to the minus alpha just times the brackets, so 2 plus 2e to the minus alpha 1 plus alpha. Let's just triple check that that's what we get from Wolfram. Oh, not quite. So if we divide through by e to the minus x, we need to do it twice, and then we have an e to the minus, yeah, okay, 1 x plus 1. No, not that. That. Sorry, I just got hit by a wave of tiredness. So we're then subtracting, because that's the whole of that term on the left. Subtracting, taking the alpha, e to the minus alpha out. Alpha times 1 plus e to the minus alpha. And that's going to give us, let's just squeeze it in here, and then we'll move the whole thing up once we actually feel that we've got the answer. E to the minus alpha over gamma cubed. 2 is the only whole number, plus 2 minus alpha plus e to the minus alpha plus alpha. I'm confused, that's what we had before, and that's not equal to 4. Apply e to the minus x times both top and bottom by e to the minus x squared, e to the minus 2x, sorry, and we get e to the minus x times 1 plus x plus 1. 1 plus e to the minus x times 1 plus x. Oh, some days I just feel like my brain's given up on me. What? Honestly, this is a bad habit, but if you're watching this, I don't. Getting to this answer is just calculus. I know I'm being stupid about it now, and I know it's really unsatisfying when a teacher's just like, you can this answer I can't find. You can find it on your own, but you can. You can absolutely find this on your own. You can. I guess one nice thing about your ability to move through time independently, especially if you're watching this later on YouTube, is that if I rub something out, like it still exists for you in a way that it just doesn't on the blackboard. You can go back and see it whenever. So let's write out this list a little bit more fully, because it'll be worth keeping somewhere. Under 1 equals a half gamma. Gamma 2 equals a quarter. I know why it is, because there's a 2 in the other bit of the... There's a 2 here, so that must why it's over... Someone's going to hear that and be like, that sounds very rude. That is an impression of Muttley from Dick Dastardly and Muttley. 48 divided by 6 is 8. Yes. So this one is minus an eighth. No. Oh, interesting. This gamma 4 is 6 times 4 is 24. And then we need to go to 48, so it's half again. We won't use these at any point yet, but it's kind of interesting. And the rest is of order x6. We don't know x6, but we know it's of order x. This is actually 0. It's not a very clear 5. Let's try that again. So, we've still got the question that I'm going to work through of why does this work for multiplication? The lambdas are just as normal to make all these numbers small. We now know that gamma 2 is a half, so this is just 1 over a half is 2. So the reason this works is that the gamma naughts are 0, which is exactly the reason why the addition works. But the gamma 1s, we're going to have, if we just do all the gamma 1 terms, we're going to have gamma 1 times, oh, that's one thing I forgot here. These need to have a negative sign. Is it those two? We have a plus b from the top one, plus b minus a. Then at the bottom we've got minuses, so minus a plus b and plus a plus b. So b plus b. Oh, this one's... Something's going wrong here. I don't know if I need these signs. If it is all pluses, then this is plus a minus a, yeah? Minus b minus... Oh, let's just... Plus a minus b minus a minus b. I need these? I can't remember. We'll work it out. It's not a blue line. So these all cancel out. Check this: 2 minus A's, 2 plus A's, 2 minus B's, 2 plus B's. Voila. Then in terms of gamma 2, we have, well, it's not so pretty. A plus B squared no, we do need some minuses here. I think I might have had the minuses in the wrong places. I think we need a minus here and a minus here. Because then these two just swap sign and this is still 0, so actually it's all these signs change, but you know, still all cancels out. Minus B minus A squared minus A minus B squared plus minus A minus B squared. Because these are all squared, we can pull out the this is the same just with negative signs, and the negative sign squared goes to nothing. So we get 2 A plus B squared minus A minus B squared, which is 2A squared plus 2AB plus B squared minus A squared plus 2AB plus minus B squared. So we get, oh, we've missed a factor. We get 4AB. And this has got to be over gamma squared. No. I'm going to keep on doing these things that are going to seem like I'm just doing them for no real reason, but I am doing them for a reason. I'm just lazy. 1 over 2 gamma squared. When we put all that together, we get our answer. And we have a multiplier. What I'm going to do is every day I'm going to just rederive this result and then get tired and stop, such that we never make any actual progress and eventually the world ends. We're not quite at making world end jokes yet, are we? So this is why this thing works as a multiplier. The right linear combination of all the terms coming out of here cancel everything but the AB term, and then we're just renormalizing it to make sure it comes out right. You know what? I don't even need that 2 there. Basically, you could argue that what I'm doing is giving the same lesson over and over again to see it get better. I think it's just this. to better understand where it needs work. Okay, I think that's now correct. The arithmetic might be slightly off, but also the arithmetic doesn't really matter. Let's have a new layer. Can I do quick transform? Can I grab this and move it? Great. Can I make it different sizes? Oh, lovely. And let's just move it a bit more over here. And we're done. This should probably be in a blue box by our rules. Because it is kind of a definition. Let's get rid of these ABs because they're sort of not there. How did we draw this in the previous one? This is close enough. So, let's start moving on to some logic, which we talked about a bit last time and a bit as in yesterday. And I'm still, in fact, I'm going to check quickly. I asked some questions on sites where sometimes they get an actual answer. At this. Also tried asking some friends. Something you quickly get to in research is that nobody knows. Well, people do know, but AI biz dev sounds good. I have no idea who are real people. It's useful when they do if they have a PhD, I'm more likely to ask them. Maybe we'll get an answer. Because I've been trying to understand. Did I ask anywhere else? I think that's the only places I asked. If I'm about to do something that there's a really good reason not to do. Because we're about to move on to a new layer. And that layer is where we start talking about simple logic. And we've been using the swish function. Now we're going to switch to using the sigmoid. Oops. Why didn't that make a mark? That's a bad way to draw the sigmoid. So the sigmoid is actually just the function we've been using before, but without the z on the top. So it's slightly on chat. Let's be lazy, and let's say that for small some minus alpha, that this is equal to I just realized something. On the previous layer I made this statement, but this is not true. This is true. we are finding this at minus alpha. Whatever happened to layer 4? So we used gammas there. Let's use betas here. So we're going to use beta alpha, beta naught alpha plus epsilon beta 1 alpha plus dot dot dot, which also means I don't need to choose a convention about whether or not I keep where I put the 2 in the next term, where, at least as it is now, beta to the n is d phi. Could be a sigma, don't know why it isn't, don't ask me. N evaluated at minus alpha. So in this language, so with this one, beta naught of naught actually equals a half. Beta 1 of naught equals half, but life is short. No, it's quarter. And beta 2 of naught is 0. So this actually fails on all of our criteria for arithmetic at 0. And in fact, with this function, there is nowhere where this is true. That's never true for this function, which is why it doesn't work, why it's not our arithmetic function. But it's great for logic. And let me start by writing down what we had last time. If greater than so actually we need to define it here. So if greater than some number, what's a good name for a number if greater than kappa? So we want something which you give it a number, and if that number is greater than kappa, it gives 1 for alpha greater than kappa and 0 for alpha less than kappa. So it's a logical check, basically. I haven't been doing it very much, but let's keep on doing it just isn't the effect I'm going for, actually. Can I make a pencil do a silly thing? Whoa, that's what that looks like. What about this pencil? Doesn't want to be that big, but it's going to be that big. Ew. That's better. It's not too distracting, is it? So what does this look like, this kappa function? Well, again, I'm just going to kind of map it out, and then you've got to work it out in your own head why it works. Just checking the kind of way that we wrote this when we did it before. Just two things coming in. It actually is a little bit more complex than this function can have variable different. This function actually depends on something. It's a function on something, and that thing is a number that we multiply this by. Oops. Which I'm going to call the strictness. And the reason I'm going to call it the strictness is that this is not 0, then immediately magically 1. It rises at medium speed from 0 to 1. But if we multiply this by a large number, that rises much quicker, because if z is 1 minus 1 here, then I look at 5 10z, well, and 10z is minus 1 when z is 0.1, minus 0.1. So this is the strictness, and is right now a free variable. And then I want to put this into our sigmoid. Remember, we were writing sigmoids as sigma of this is equivalent to again, to the sum of the inputs minus alpha. I'm not making this any clearer, am I? Drawing more boxes around it, that'll do it. And we're going to compare this at kappa. And this will give, it'll give our answer. This is not a particularly complex function. In fact, you could say that this just is the sigmoid. We don't need to renormalize by s, because whatever comes out is somewhere between 0 and 1. And the degree of accuracy depends on on this. We also don't want it to make it into a small number. In fact, s can be quite large. The larger it is, the more discrete the step. So big S looks like. Boop. That should be even either side. And then smaller S's go slower. That's a bad drawing. Look it up on Wikipedia. It's better explained there. So this can take as many inputs as you want, and you can actually reweight them as you want. And it will be whether the weighted sum, whether the weighted sum of everything is bigger. It'll just give one output, and that output will be a number between 0 and 1. It'll be the output of this function. We've just got one. You might want to ask, if a number is significantly greater than itself. So you might do kappa of kappa. Why do you do this? Well, it's still 1, 0. That just means that the weight of the strictness we're putting on is kappa. Which will mean that if kappa is a significant, if kappa is like, if the number you're putting in is like 1.1 kappa, you'll get pretty much 0.5. So this is roughly a question of, is the number significantly different? There's a variety of reasons why we use these continuous functions rather than discrete ones. The biggest one being that these have gradient always, and so if you're learning by gradient descent, this is vital. Right, now finally at 2 p.m. I'm getting to new stuff for the day, and I'm going to take a short break before I get into it. Just possibly check some email quickly. Update for National Express coach services suspended. I should read this properly later. Oh yeah, sorry. Let's just see what the university is saying. It's probably exactly the kind of thing that you're not supposed to share. The university is still, oh no, a Cambridge professor has passed away. It's still kind of on the fence about whether it's doing assessment. Yeah, it's not very interesting update. Oh, I don't have an account for this. Go away. Alright, yeah, I'll be back in a moment. Um, so another way of saying this, I was just thinking about ways to express this. Let's draw a nice diagram actually. So here is phi of. We're not actually using these properties here, I should say. Can I just grey them out? If I just do this a bit. This is a bad tactic. Because we're not making the assumption that epsilon is small at any point here. In fact, that's exactly what S is changing. So this is, again, changing S of Z minus kappa. If kappa is here, and this is Z, this is a rough picture of when, do kappa about here, of S is roughly equal to kappa. This is S is much larger than kappa, and in the limit, when it's really large, it will just look like a step. And then if you wanted, if you were so inclined, you could have an even softer boundary with S much less than kappa. No, this isn't quite right. To rethink this again, this is kappa over S? I think that's a better way to do it. Well, no, it's S kappa. Huh. What a world we live in. What a time to be alive. S kappa. So this one is kappa squared. Yeah, because this then comes out as, let's draw this again, let's draw it bigger, let's draw it better. Let's make it really clear. Can I have, that's unrelated. I was trying to see quickly if I can have a grid to draw on. So I want this to go to large values. This is Z, and this is phi of S, Z minus kappa. Sounds a bit like oh, I've just seen that you can't see. So where it is, let's end it there. So Z. Sounds a bit like a Katamari tune, this one. No, never that. So this is value of 1. Kappa, 2 cap. 2 kappa, 0. That'll be enough. God, every time you end up down there. Oh, I see what keeps happening. Every time it goes to black, it loses its kind of memory of ever being blue. So let's start with the pretty dark, with a really high S. It's going to go through that point. It's going to come up and look something like that. So this here is S much larger than kappa. Then I want lighter and bluer. It's going to come through here. It's going to kind of be visible. Not that visible, but a little bit more visible from further out. And this is S, about the same size as kappa, and honestly, this will just look like a straight line, almost flat line, but there is this intermediate, like, that's probably a bit too subtle. There we go. This is S, much less than kappa. Let's get rid of this being in the way. So we don't have a really discrete on-off available to us in network architectures. We have to make do. So this is I've called it a 0-1. It can only act on a single input though. So I'm going to call it a 1-1. I'm wondering if the system is still self-inconsistent. 1, and it's just a single logical node. Okay. More logic. What would we like to do next? This is where we can start delving into unknown territory. What about a... Oh, by the way, I should say... all you need to do is change the value of S change the sign of S, and this goes from being a greater than to a less than, with exactly the same behavior. So, what about a equal to? What if we want to check if two things are equal? A and B. No, let's first have a programmable if. A and B. So I want a function which tells me if A is greater than B. We need a name, we need a different notation for these logical functions, don't we? By curvy top. So this takes in two inputs, and it's going to give out 1. We don't yet know this. That's what we're going to work out by finding this, and it's going to be 1 if A is greater than B. 0 if A is less than B. I think maybe I'll use just dots on this. I like how much that looks like a face. Yeah, I'm in. Now we're doing logical functions with dots as their arguments. This isn't programmable. It truly is greater than a certain function. So I'm not going to change the notation on that one yet. But this just looks cool. Actually, I kind of want to get rid of that little. No, it's so not worth it. So we're going to feed these in, and it's going to give us out one of these two conditional cases. Now, how can we do this? What this is equivalent to is a we want to feed A into a greater than B function. So we want a programmable greater than function. So this is going to oh cool. This is just these guys go into a negative of this. Go into a 0. Positive this, positive this. Let's add a step just so that we can have our strictness again. So again, that will and then we get indeed this. So you can compare two numbers pretty easily. It's actually no more work than just comparing one number. So now we could ask, let's call this compare to. Now I could ask for a max function. See, I told you we were going to actually program something. We want A, B, this still has this programmable strictness. That eventually just becomes kind of the reliability of this function, and that is a learned thing. Why are these lines so ugly? So it's still logical. It's a max of 2 inputs. It might be a max of more than that, but let's start with that. In fact, I'm going to call it 2 max. Two max is a really bad idea for a thing to call a function that you're going to put into any programming language, because programming languages hate to start words with a number. I'm constantly like, I don't know if what I'm doing here is at all useful. So we're taking in 2, we're giving out 1. Those two are A if A is larger than B, B if A is smaller than B. So, I think I know the form for this. I think it's going to be this. That's not how I draw that anymore. This might not be the most efficient way to do this, but this will work. There's a few different ways I could do this. Let's try this one first. So these are all one width, one height. Well, I've done these because I need to keep values of these. So this is now our value of 1 or 0, depending on success of that question, basically. I've been being a bit loose about this, but let's... I find it way easier to understand these when these are filled in, but that is a bit dark. So now we know which one's bigger, but we don't actually have the value of them yet. If we multiply this, this is our 4, 1. Then we get something that is A if A is greater than B, or 0 if A is less than B. Now if we do the same here, no, actually I need another step. I'm going to go down onto the next line so that I don't take up too much of the screen. I want to do 1 minus this number. To do 1 minus a number, you actually have to have a 1. Which is easy enough to make, and I'm just going to invent one. I think it's fine to just invent ones and just say that, okay, the network doesn't need to make this one, but it can just be stored somewhere. That one I actually want to be down at the bottom, so let's swap the B and the 1. No. I probably don't even need to bother drawing the identity on these because I am just passing them layer to layer, but I think it's good to keep them in mind. Yeah, actually, particularly because it does actually take A. So I want a 1, and I've got B through to here. So now I'm bringing the 1 in. The reason for that is that I want to do one minus this into a plus. Oh no, I can do that. Yeah, no, I can do this straight away. Okay. I confused myself. I just do need this 1. Let's make this go straight across. Basically going to go back to how it was. It's a whole new way of thinking this. Whether it's a useful way of thinking remains to be seen. But, you know, it's an interesting challenge. I'm enjoying it a lot. Because I want this to go up here. And I want to do a multiplication. That is just something on this playlist, but that's not how I draw those anymore. I have moved on. So again, this is a 4, 1. This is it's a 2 to 1. I'm not going to bother drawing that. This is the more important thing to draw in general, I think, we'll find. Then I want to put these two into 1, minus and a plus. But I can feed that directly into a multiplicator, I think. A multiplicator? The reason being that this gives... I know I've drawn this so many times now, but let's make it nice. Nice one's nice. So I'm going to bring this up here as well, and then I'm going to minus that plus this. So this is 1 minus this. So when I multiply these two into b, I've got something that is up here. I've got something that is a if a is greater than b, and 0 if a is less than b. And here I have something that is b if, that's 0 if a is greater than b, and b if a is less than b. So now all I need to do is add them together. And I get back out a if a is greater than b, or b if it isn't. So let's just got this layer, and this is the end. So a if a is greater than b, and b if b is greater than a. And we'll just shade in the between nodes. And voila, we have a maximum of 2 number finder. It's not beautiful, but it works. Is that really true? This step here is worrying me a little bit. It is. I think you can put those in there. I think maybe it does need another step to add those two together. I'm gonna write it down as if this is fine, but let's move. Oh no, you're not a highlighter. There we go. This is a question mark as to whether or not it should be an extra step. So how many steps does this take? There's 3 on this layer. Then, here, there's 4 and 1. If that isn't valid, it's actually a step before that which has one identity, 2 identity, 3 identity, 4 identity. I think you do need that step. It's either, so I think it's this, 4, 2, 1. If that's valid, then this is 3, 8, 2, 1. If it's not, then this is 3, 4, 8, 2, 1. Annoyingly, this layer is 3 identities. And 1 addition. Regardless, I think we've done something pretty powerful here. We've shown that a neural network can, these are all just width 1, that has this number of nodes. So this is a network which looks like 2 feet in. Those nodes look like sigma swish, sigmoid swish. Oh, I'm just going to draw them like this. Let's draw this again from scratch, a bit neater. So kind of zooming out, we're showing that this can be done with. I maybe should have different notations for these. 2 sigmoids and a logic. Then I think we do need that identity layer. So all sigmoids. You know what? So that these don't get confused. Let's draw them like this. Then we've got 8. Um, 2 more. And 1 more. So this network with everything can be connected, not all of it actually has to be. With the right weights. Let's both go to here. You go to that. You go through, but you also go with the 1 that we're going to bring in. Oh, it gets ugly, and we do also have this 1 injection. That is scary. I've got trying to draw all of that. Let's get rid of all these little lines. Because it just gets. This is kind of why we're doing this whole exercise. It gets too complicated. But in theory, a network like this could find the maximum of two numbers regardless of the two numbers. One thing I didn't touch on is the degree of strictness of these. It's an interesting question, actually. A question I'm just going to leave for later. Okay, let's do a little bit more logic things. One thing that I think that I'd like to look at is more logic, specifically equal to. Again, this is going to be an approximately equal to, but let's start with an equal to k, to kappa, and then we'll do an equal to two different numbers. So is A equal to kappa? So at least partly logical. Oh, I'll tell you how I could write it actually. Maybe the better way to write this is that this is this layer. It needs both, although it only needs this in one place. So it needs one and it needs 2, 4, 8, 2, 1. And this way, it's a little bit smaller so I can actually do. This way you can capture all the information about what kind of nodes it needs. In fact, I'm going to propose that logical nodes just sit up top. And if they're only logical nodes, I'm going to do a wiggly line. Who knows what's going to look clear in the end? So, I want something which is 0 if this is truly an equal to. If this is not close to kappa, and is 1 if this is close to kappa. You know what, I should have defined this before. This is a worthwhile logical thing. logical inverse is probably a kind of function worth just writing down. It takes a number, I'm going to call sigma, because why not? I haven't used it anyway. Between 0 and 1. And the number 1, and it just does a addition operator on them. That's not what addition operators look like anymore. Everything is a pipe. And you get the inverse of sigma, which is still between 0 and 1, but now if sigma was 0 before, i.e. false, it's now true, the inverse is true, and vice versa. So this is basically the function we used in the previous example, where we had this like pulling 1 in from nowhere. If we wanted let's actually write out clearly what this is. This just gives 1 minus sigma. If we wanted, we can generate a 1, I think. Gen 1, which just takes any number and puts it through a sigmoid with a sufficiently multiplies it by a huge number and then puts it through a sigmoid with a negative sign. And that will always give 1 for oh no, we would need that number to be greater than 0 for that to work. From day drawing. So for this Gen 1, if we know that there's a positive number in there, this isn't great then. We want to make this as unconditional as possible. No, it's better to just have a huge bias. right at the beginning of this, I decided that lambda was going to be very small. I could have decided it was going to be very large. Life would be much easier. But this will work. That'll give a 1, always. This does assume that so it's not perfect, but we have a way to generate 1, and it just creates 1 extra step. It might be a good idea for any network which has a logical operator in it to just insert a 1 at the level before. Okay, so now we have the ability to generate 1. This again is a strictness kind of thing, because if A is, so let's just check what we've got already. Let's compare to so one way to do it, this is kind of lazy, but this is how I'm going to do it, is we can multiply the results of A greater than K, kappa, and A less than kappa, and then multiply that by 4. So these feeds directly into multiplication. And the reason I've said that is that these are going to be close to a half if these two are close. So that will tend to 1 if A is close to K, it's kappa, and 0 if A is not. With, again, the strength of these weights, the strictness of these weights, specifying that. So that would be a, these are 1s, that's a 4, 1. So that would mean that this was a 1. That's not how I'm drawing these anymore. Nothing sigmoidy on the first layer, then a 4, then a 1, and on this layer we need 2 of these, and then nothing sigmoidy. Nothing, nothing swishy on this layer. And if we wanted to do two numbers equal, we could just do a compare two in the place of these individual comparisons. Let's just see what that says. It's got two equal. That's AB going into our friend and his friend. And then going into the multiplier. Then that same factor of 4. We get to our answer. So 2 equal is a this takes in just 1, goes to 1. I don't even really need to say what they go to, do I? Unless they come out early. This takes in 2, goes to 1, and same, no different. Do I want to do any others while I'm here? Not equal is just this, then a logical inverse, so that's just adding one sigmoid step and chucking in a gen 1 to generate R1. So gen 1 probably always needs 1 from the layer before. I think finding a min would be the same as, oops. It reassures me to have that dot there. I also like the idea of putting in the plus when we have to generate 1. I really don't want this language to get too arcane though. Let's leave it out for the moment. Is there a better way of doing 2 equal? Maybe that's the question I'll set myself for the moment, because that's alright, but it's 3 layers. One question that's been weighing on my mind a lot is if there is any way to get a. Stop chewing on this. To make a sigmoid out of swishes, or vice versa. Just out of interest, can we do an n equal? What would that look like in comparison? I think we would need to logic check every pair. A, B, C. So we go to Z. I think we would need to do 2 logic checks times number of pairs. Then we would need to do, which can all be in one row, log 2 I'm going to call this lim plus of 2, meaning that we round up if it's not a whole number, times the multiplication operator, and then we need to multiply everything by 2 to the n pair. I guess an interesting question is, can we multiply more things? More efficiently? Because if we're using this multiplication tactic, then that's going to be important. I've just realised that if we want two things to be equal, we can just check if their value is close to a half. With more strictness. The more I play about with this, the more I'm like, wow, this is going to be quite difficult, but also potentially really useful. I think I'm going to leave it there. Hope you've enjoyed. Bye.